in this case, it didn't talk about anything about the fringing flux to say there is a fringing flux. Basically, AG and AM, they are the same, right? How much is the AG, AM? Depth is 2 centimeter, right? Right? And here is also how much? 2 centimeter. So 2 by 2, right? It's going to be 2. So you know G, you know LM, you know mu R, you know all these values, right? So you can calculate the flux in this circuit. How much is the flux? Ni over Rg plus Rn. How much is the flux? dA. How much is B? We said we want to have 0.5 times 4. Right? So you know Rg, you know Rn, you know flux, you know N. You can calculate what? A current, right? You could calculate that. That's one case. The second case is here. I'm going to leave the rest. You can calculate yourself. The second case, if I will have connected this way. Right? This is the IV. Right? Current I coming, IA and IV, they are the same, right? IA and IV, they are the same. Basically, this one is going to be equivalent to what? 230. So basically, you solve everything, but instead of putting in 500, you put in how much? 200. Everything is the same, only you put the current out and 200. Now I'm going to give you a homework for yourself, not homework, practice. If they are parallel, calculate. You put them in series, right? Put this coil in parallel and connect the voltage source. Let me go a little bit further to tell you. Let me go a little bit further. And the other part is saying calculate the inductance in the system. Inductance. So how much is the L11? Let's say LA. Here, LA. How much is the LA? I'm not going to calculate it. Just tell me quick. How much is the LA?
3.2.
R equivalent, right? How much is the R equivalent? Right? How much is the LV? The second part said calculate the self-inductance of each winding. How much is the LV? How much? It didn't say to calculate it so much. How much is the LAB? For case mode, how much is the LAB? How much is it for the second case? Say this is case 1. For case 2, how much is the LAB? Can you tell me? What money? Fluxes are the opposite of each other. when the flux is opposite, they're going to reduce the flux, the overall flux, right? Think about it. When you think about it, it says lambda 1 is L11 I1 plus L12 I2, right? And we said lambda 2 is L21 I1 plus L22 I2, right? Case 2. Look at the case 2. If I didn't have a winding B, my flux is going to be more, right? Because see, for the case 3 now it looks like 200. A by itself is 350, right? If I didn't have the B, I'm going to have more flux, right? Because my current is 350. Basically, the winding B is reducing overall flux, right? So how that one can happen? See, this is the flux, right? This is just for winding A, right? Now the result is less than this much. How that can happen? Only if this one is negative, right? Only if this one is negative, right? Case 1 is equivalent up to how much? 500 terms. It's more than what A itself can generate, right? Basically L12 is positive, right? So that's the reason I'm saying here, for case 1 is positive, for this one is negative. Now, if you want to calculate the force and those kind of things, you can calculate it. But do it for the parallel. Parallel connected to a voltage source. Assume these two windings, they are parallel, connected to a voltage source. Calculate the force.
Can you draw it?
Yeah, parallel is that. Voltage. See, I'm putting this is important. Voltage source, not current. Voltage. Think about this. If they are parallel connected to a voltage. You want to put two more examples? We'll do it. We can solve. If you want, we can solve one more. And then if one, you can also up to you. I think I want to draw only one thing for you guys. This is a problem 1.6. I'm not going to solve it. Just I want to because I like this one to see how in the real electric machine. See, we went through all these magnetic circuit and everything. Just you will see in the real machine how the magnetic circuit is there. You know, even if there is an inductor, simply you can say, okay, the current is going to go through here, and this is the flux and those kind of things. But let's see. I want to draw this one because I'm going to use it for a DC machine later also. I'm not going to solve the problem. This is the problem 1.6. I think is a DC machine, but it has a cross section like this. I should do full circle, so I'll divide it back. So if you look at all this machine, you can see there is a cylindrical, cover, right? That's this one. And this is all iron. This is all iron. I'm talking about DC machine. What the DC machines they call this one the state because it's not moving. Usually it's fixed on the bench. Is the screw to the bench and it can move. This part is the rotor, is the moving part. This is another part. DC machine, they have an excitation system. You will see it in the lab. When you go there, you can see there is an excitation winding. They connect this one to a source, we call it VF. V fill. That's the voltage we're going to put in the motion. And I'm going to talk, for example, about the generator. It's very simple. On the generator, they have a windings here. And they have a brushes, here. I'm not going to talk about the structure later. I'm going to talk about it more. But this is a DC machine. For example, let's say this is a generator. What's the difference between generator and motor? Can you tell me? Generator, the mechanical is the input to the system, right? Mechanical power is the input. You rotate the rotor, right? You generate electricity, right? And in the motor, you connect it to the power, to the electrical power, and you move the mechanical load, right? If you look at the rotor of a generator, let's say if the machine is rotating like this for a generator, mechanical torque is like this because we rotate the machine, right? The mechanical torque is the same direction with the direction of the machine. Electrical torque is like this, right? If it's this is the motor. If it's a generator, sorry, this is a generator. Sorry, this is a generator. If it's a motor, let's say the machine is rotating like this, right? Motor, when we have a motor, we plug it to the wall, it starts to rotate, right? Electrical torque is rotating the machine, right? Mechanical load always is going to stop the machine, right? Now, look at this system. This is, let's say, assume the generator. Generator, basically, this rotor is connected to a shaft and is rotating by a prime mover. It could be a steam turbine, it could be a hydro, it could be anything, right? The middle part is moving. Now, all I said here, I want to talk about the magnetic circuit of this system. If you look at here, the flux, look at it here, this is the current direction. This is the I, right? So this one is going to be I, right? They are roughly wrong. No, that's correct. If you look at this one, because this one cannot be against this one, because if you put them in the wrong direction, they're going to cancel each other. There is no magnetic field. So this one is going to generate the flux this way, right? And again here, we're going to have the flux this way, right? So the flux is going to be this way, right? P. And if the circuit is, if the circuit is symmetric, which it is, almost half of that is going to go this way, half of that is going to go this way, right? Half and half. Here, the flux here is going to be radial. I mean, it's going to go in the same direction of the radius of the rotor, and it's going to come inside, and it's going to go radial back. And here is like this. And this is the flux. Half is coming from here, half is coming from here. Now I want to draw the magnetic circuit for this.
What does it go radial?
Radial is the theory of that. It's the electromagnetic theory. I'm not going to take you down, it's going to take a lot of time. Just I want to finish this one for you. We can talk about that after this. So look at here. I want to put the magnetic circuit for you. I have one winding here, one winding here, right? So it's going to be just I want to tell you whatever you are saying here is going to apply to electrical machine, One here, and it's going this way, Ni, and another one here, Ni, right? I'm going to have one part for here, one resistor for here, one resistor for here, right? Let's call it R1. Right? I'm going to have two air gap resistance here, right? Let's call it RG and RG. I'm going to have one in the middle because of the iron of the rotor, right? So it's going to be RR, right? I'm going to have one here and one there, right? So it's going to be like this. Flux is going like this. Half of P is coming this way, half of P is coming this way, and this is, for example, R2, R3. So that's the circuit for that electrification. That's the circuit. This circuit is easy because the rotor is cylindrical. This rotor is cylindrical. You can see it doesn't matter what's the position of this one, right? It's here. Let's say this is the axis of this one, right? This one is rotating, right? All the time the air gap is constant because this is cylinder, right? There are some machines, they call it solid pole machine. The rotor is like this. The rotor is like this. The rotor is like this. Now, if it's here, look at that one, the air gap is this big, right? When it rotates this way, the air gap becomes small, right? When this one rotates this way, 90 degrees, they call it solid pole. Just I want to give you a little bit of information. It's still the same idea, a little bit more complicated. But this is a magnetic circuit. What we talked about the magnet. This is a real motor, and it has this magnetic circuit. And we can go calculate the flux. We designed this machine. This is all the design part now. You say I'm going to use this kind of material, so the B shouldn't be more than 1.4. You go calculate number of turns and those kind of things to make sure you're running the saturation part. I wanted this much torque. So you can calculate this one. If you put this much turn, you're going to get this much torque. This is all the design part. Next class, Tuesday, I'll show a little more examples on this course for the rotational machine.